All right, hey there, Earth Science students. Here we're talking about minerals and mineral identification. So let's get to it. So first off, what is a mineral? So a mineral is a substance that is naturally occurring. So it has to occur in nature. This mostly means it is not man-made. It has to have a definite chemical composition. So that means that if a particular mineral is made out of, sodium and chlorine, it's always made out of sodium and chlorine or a certain set of elements. The atoms have to be arranged in an orderly pattern. We call this a crystal. So this is what we're going to see is going to give the minerals their properties. It has to be a solid. So there are no liquid minerals. Once we melt it down, it is no longer considered a mineral because it no longer has that crystal structure. And it has to be inorganic, which means that it has to be something that was never once living. All right, so minerals are a non-renewable resource, which means that once we have mined them, once we take them out of the ground, they will not be replaced within a human lifetime. So they are not something we're going to be able to get more and more of. Once they're mined, that's it. So minerals are going to be identified based on their physical properties. So those are color, luster, streak, cleavage versus fracture, so the way it breaks, hardness, and any unique properties the mineral might have. So I'm going to go through these and show you how we can use each of these to identify our minerals. So the first is color. It's the most observable, right? It's the one that we see the easiest, but it is actually the least useful. Why? Well, these are two different minerals right here. The one on the left is fluorite and the one on the right is quartz, but they are the same color, right? So if we were just going to go with purple minerals are always fluorite, then we'd be wrong, right? This wouldn't give us any information. So minerals can often be the same color. One color that pops up all the time is white. Lots of minerals are white. Halite, calcite, gypsum, feldspar, quartz, dolomite, talc, all these different minerals are white. So just by going off the color is not going to tell us a whole lot about what the mineral is. The other thing is, one type of mineral can be multiple different colors. This is all different varieties of quartz right here. It's all the same mineral. The reason why it has different colors is slight inclusions in the crystal structure of different elements and different things. So that's going to give them a different color, but it doesn't change what the mineral is. So once again, using color is going to be super unreliable. Luster. So this is the manner in which light reflects from a mineral surface. So we got two that we're going to be talking about in this class. There's actually lots of different types of lusters, but for reasons of our science, we're just going to focus on two. And we're going to call them metallic, which is one that looks like a metal. Think about a coin or anything like that that's going to look like metal. And non-metallic. So this is anything glassy, waxy, pearly, earthy, anything that isn't a metal. I usually say if you can see through it, it has to be non-metallic. That's one of the dead giveaways for non-metallic. If you can see through it at all, if it's at all translucent or transparent, it's non-metallic. Then if it looks like a coin, it's metallic, right? If it looks like iron, it's metallic. Even if it's really dark and it still has that kind of metally shine to it, that means that it's going to be metallic. I often try and say, even though I just said metally shine with it, shiny doesn't mean metal, right? Glass can be shiny, mirrors can be shiny as well. Doesn't mean that they're necessarily metallic. So I just want you to think of coins, think of keys, think of anything you know that is a metal. If it looks like that, then it's a metallic mineral. All right, streak. Streak is the powdered form of a mineral. And you perform a test in order to find this. So oftentimes we're going to find that what the mineral looks like is not necessarily what the streak is going to look like. So I'm going to show you an example of somebody doing a streak test right now. All right, so you can see they got a bunch of minerals here. They're all different colors. They all look very different. And they're going to perform a streak test. They're going to rub this mineral on these ceramic plates down here to see what the powdered form looks like. So we can see this first one. It looks white, right? They're going to rub it onto that black streak plate right now, and we're going to see that the streak is white. It matches what the mineral looks like. All right, now you can see we've got a piece of fluorite here, right? It's kind of green. It's not a white mineral. You can see it's kind of got some white at the edges. Let's see what its streak looks like. So first they rub it on the white streak plate, and they don't see anything, right? Nothing shows up. So you might put this as no streak. Then they rub it on the black streak plate, and what do they see? It's a white streak. Now that mineral was clearly green. It's not the same exact color as the streak. So sometimes the streak is not necessarily going to match exactly what the mineral looks like. All right, here we got a piece of hematite. So we're going to see what the streak of this one looks like. They're going to take it and they're going to rub it on the white ceramic plate. And you can see that it has like a reddish brown streak to it. It's not that dark color that the original hematite was. All right, now let's look at breakage. So this is cleavage versus fracture. So cleavage is going to be when a mineral breaks in a predictable pattern, and fracture is going to be when a mineral breaks in along uneven edges or a unpredictable pattern. All right, so here we go. We got an example of somebody breaking up a chunk of galena. Now galena is going to show cleavage. You can see when they hit it with a hammer, it breaks along weaknesses in the crystal structure, and it breaks these nice even planes. They're nice and flat. This mica right here, this is going to break apart. He's going to peeling it with a knife. So once again, these are going to be weaknesses in the atomic structure and the crystal structure of the mineral that's going to allow it to break easily along these planes. So you can see they fit the knife right in and just kind of peel it back. Now this is common in all the micas, biotite, muscovite. They're going to peel off in these sheets. I want you to think about like it's easier to, if you had a stack of paper, to peel one off the other than to kind of tear them in half. So it's much stronger going the opposite direction. Now this is a chunk of halite right here. They're going to break it. It's actually going to break into cubes. So you're going to see that it's going to break along those nice cleavage planes. It's going to break along those nice faces. Yeah, pulls the chunk off right there. If you ever see the salt on the ground, when they're salting the parking lot, you'll see that it's little cubes just like that. All right, here's an example of fracture. So you can see this is really jagged. It's not breaking along nice, even planes. Even though some of those edges look a little bit flat, they're not going in the same direction each time. You can see it's kind of breaking apart like glass. All right, the second to last property that we're going to be looking at is the hardness scale. So how easily a mineral can be scratched is where it's going to reside on Mohs hardness scale. This goes from 1, which is talc, which is the softest mineral, all the way up to diamond, which is the hardest mineral. Now, the way this chart works is that a mineral with a higher Mohs hardness number will be able to scratch everything that's below it. So for example, fluorite right there at number 4 is going to be able to scratch everything below it, calcite, gypsum, and talc. It will not be able to scratch anything that's above it. So diamond gets to scratch everything and talc gets to scratch nothing, being at the top and the bottom of the Mohs hardness scale. Now there's a couple of things that we can find that can help us to kind of test these things out in the field. So for example, a fingernail has a hardness of 2.5. Right, so that means that talc and gypsum would not be able to scratch your fingernail, but calcite can. A copper penny has a hardness of 3. So once again, talc and gypsum would not be able to scratch you a copper penny, but everything above 3, fluorite, apatite, orthoclase, and quartz, would all be able to do that. Glass plate has a hardness of 5.5. So anything that is below 5.5, so apatite on down, is not going to be able to scratch that glass plate, no matter how hard you press. But everything above it is going to be able to scratch it really easily. All right, another thing that helps us identify minerals is their unique properties. So these are all listed in your reference table. If a mineral is going to have a unique property, it'll be there. So for example, magnetite is magnetic. It's in the name, right? You can put a magnet on a piece of magnetite and it will stick. Halite is going to taste salty. It is salt, right? It's the same stuff that we put on our food, the same things we crush up and put on the roads. Phosphorus will glow under black light. And calcite is going to bubble with acid when we put hydrochloric acid onto it. That's one of the biggest tests for calcite. So what determines all of these things? It's the internal arrangement of atoms. And I want you to remember that phrase. They're going to use that throughout this unit. The internal arrangement of atoms. That's what gives all of these minerals their different properties. From their breakage and hardness to unique properties, all the things are determined by this internal arrangement of atoms. So, how can two minerals be made of the same thing, but be very different from each other? Graphite and diamond are a classic example, right? Graphite is super soft. We use it in pencils. Diamonds are the hardest known substance on Earth, a naturally occurring substance on Earth. And it's because of the way that their crystals are shaped. They're both made out of carbon. They're made out of the same exact type of atoms. But hexagon atom, crystal structure, is going to be weaker than a tetrahedron. right? The tetrahedron is going to kind of link together and it's going to create a very strong substance. Whereas the hexagon, they're going to kind of slide past one another. They have weak bonds in between each of those hexagons. All right, and finally, all this information can be found here on page 16 of your reference table. It's the very last page of the entire reference table. We have mineral names all the way over here on the right, and all of their properties are going to the left, as we can see. Now, there's two big categories that we separated them out to begin with. That is luster. So we got metallic luster up here and non-metallic, which is most of the minerals that we're going to be looking at. They're mostly non-metallic. So that's a great way to kind of, if you look at a mineral, quickly separate a big group from a small group, right? If I got a metallic mineral, I only have 5 minerals left to choose from, right? I don't have as many to choose from as if it was a non-metallic mineral. Then they are arranged from softest to hardest within that luster. So the softest one right here, talc, is at the top of the non-metallic right here and goes all the way down to the hardest, which is garnet. We also have cleavage versus fracture. If it has a check on the left, it shows cleavage. And if it's on a check on the right, it's going to show a fracture. Then all of those unique properties and all the other things can be found within, right? We've got distinguishing characteristics, common colors, and uses. And then finally, our composition. So what elements is it made out of are right here. And if you need to know what these symbols, these chemical symbols are, we got them all down here at the bottom. All right, and that does it for minerals. We'll be moving on to rocks next.